Here's some interesting news for the fellow space junkies out there. Astronomers discovered the largest ultramassive black hole ever seen, or at least the largest that they've seen so far. This was just published today, even though they first discovered this galaxy, which I believe they call the Horseshoe Galaxy. It was first identified back in 2007. And let's see here, astronomers, they've uncovered what may be the heaviest black hole ever directly measured, located at the center of a galaxy nearly 6 billion with a B light years away. This ultramassive cosmic monster is estimated to weigh in at 36 billion times the mass of our sun. So essentially, the size of this black hole, the mass of it is equivalent to our sun times 36 billion. So it's really hard to wrap your head around it. Humans have a difficult time trying to measure anything in terms of billions. I mean, we just can't comprehend that number that is so massive in size. So this discovery, it was made in the foreground galaxy of a rare gravitational lensing system known as the cosmic horseshoe, which was first identified in 2007, and that's what they're referring this to. So what you're essentially seeing here is a galaxy here in the center. It looks like a star, but it's not. This is a collection of probably billions of stars, and this ultramassive black hole is at the center of this object, and this horseshoe shape around here is actually a different galaxy that is actually positioned right behind this galaxy here. So I actually have an animation because it's difficult for me to explain personally. I'm sure other people could explain it a lot better. So I came across this animation, which can show you a good idea as to what is happening here with the distortion of light. And I'll just go ahead and play this for you. I don't believe there's any sound. So you can see the light being bent by that galaxy, and it actually shows 4 quasar images in this animation. Now, we're not looking at a quasar in this horseshoe. This is not a quasar. It's actually a galaxy. A quasar is a single object. It's a quasar essentially is matter being ejected out of the north and south poles of a large black hole. But this animation, it's not necessarily showing the effect of a galaxy per se. Instead, it's showing you what the effect of it is. So imagine this to be a galaxy and not a quasar. So the light from the galaxy is traveling toward Earth, and there's another galaxy in front of it between Earth and that galaxy. And the gravity of that galaxy is bending light around it and curving it back toward our position at Earth. And that's essentially what's happening in this image here. And with that being said, I've actually got an animation of what it actually looks like if you were to put this image in motion. So imagine the camera moving from left to right or the other way, either way, and you can see this lens kind of curve as it moves. So I'll show you an animation of what I'm talking about here. This will give you a good idea as to what gravitational lensing is. These are all galaxies, and you can see as the image is moving, these objects are galaxies that are right behind the center here, in the center of this image. And what it's doing, the gravity of these galaxies are actually lensing the galaxies behind, making it possible for us to see those galaxies behind those galaxies in the foreground, which is pretty amazing. It's an awesome phenomenon. It's really cool how nature allows that to happen. And it makes even more sense that it's so strong in this image that we can actually see details of this galaxy. And this image isn't probably a single image of the galaxy. Rather, it's probably 3 copies of that galaxy. Now, this is an actual natural image that Hubble and probably James Webb also took. And they actually, those cameras actually observed this image. So my guess is that this is probably an image of it. That might be another, and this might be another, possibly the center of that galaxy. Much like what's happening in this effect here, where you see there's one quasar, and then when you move it around, it actually projects an image of 4 quasars, but there's not 4 quasars, there's only 1. The gravitational lensing effect produces 4 of that same image, which the quasar is right behind that galaxy. And the gravitational lensing allows us to see it. Not only we get to see it, but we probably get to see it even closer than it actually would appear otherwise. So if you get rid of this galaxy and you just observe the quasar behind it, it would probably appear way, way smaller than it actually appears in the actual image. Like almost like a a magnifying glass, basically. So I saw that to be really interesting, and that's the effect that this is having here. So, and especially with the ultramassive black hole being so massive, that gravity from that black hole allows that curvature to be so strong, with having the mass of 36 billion solar masses. That is insane. So anyway, the new research led by Carlos R. Melo Carneiro from the Institute of Physics at Federal University of Rio Grande do Sul used a combination of gravitational lens modeling and detailed stellar dynamics to pinpoint the ultramassive black hole lurking at the center of the lensing galaxy. So what is the cosmic horseshoe? The cosmic horseshoe is a near-perfect example of a gravitational lens, a phenomenon where the gravity of a massive foreground galaxy bends the light of a background galaxy. And here it is again. That's just a different image of it. Let me see if I can scooch this over. I'll put it over here to the side so you can kind of get a view of the image as I'm reading this. In this case, the background galaxy appears as a luminous arc encircling the lensing galaxy, forming what's called an Einstein ring. The lensing galaxy, named LRG 3-757, is what astronomers refer to as a luminous red galaxy. This is a giant elliptical galaxy that shines brightly in infrared light and contains very little star formation. The reason there's not much star formation here is because that black hole at the center, it became so massive very early in the universe's age, where it gobbled up probably the majority of the gas, the dust, the stars, just the matter that's inside that galaxy was swallowed up by that black hole, which allowed it to become as large as it became. And that happened pretty early in the universe, in the universe's age, which pretty much hindered this galaxy's ability to coalesce into a spiral galaxy. Instead, it just remained as an elliptical galaxy. And probably through the result of other galaxy mergers early in the universe, this galaxy was probably gobbling up all kinds of galaxies nearby. And these galaxies, when they keep smashing into each other, merging, colliding, it just, if they were spiral galaxies at any time, it just ripped them to shreds, and it pretty much left it as this just ball of stars as it appears now. So you don't really see any gas, any dust. It's just a collection, most likely very old stars that are just sitting in this galaxy. Probably fairly calm, I would say now, pretty stable, I would imagine, even though that this image was taken, this galaxy, I believe they said it was 6 or 7 billion light years away. So we're actually looking at this galaxy as it was 6 or 7 billion years ago. So it's probably even a lot more stable now than it was back then, because this image was only about from the time the universe first happened at the Big Bang to right now, that was about halfway in between the Big Bang and today. So pretty old. Very old galaxy. So anyway, LRG 3-757 is not only huge, it's about 100 times more massive than the Milky Way, but it's now also known to host one of the largest black holes ever measured. Now, black holes, especially the largest ones, are notoriously difficult to measure. Researchers typically rely on the motion of nearby stars and gas to estimate how much mass must be present to account for their velocity. But at vast distances like this one, over 5 billion light years away, 5 billion light years, direct observations are challenging. Milo Carneiro and his team took a different approach. They used detailed data from the multi-unit spectroscopic explorer, or MUSE, instrument on the Very Large Telescope, paired with high-resolution images from the Hubble Space Telescope to create a combined model of the galaxy's mass. The key innovation was incorporating both the gravitational lensing distortion of background light and the motion of stars within the lensing galaxy itself. The result was a precise mass estimate of the central black hole, weighing in at an astonishing 36 billion solar masses. That is insanely huge. Beyond what was thought possible, astronomers have long known that supermassive black holes lie at the center of most large galaxies. Their masses tend to follow a predictable trend based on the speed at which stars move in the galaxy's center, a relationship called the MBH-OE relation, where OE, I don't know if that's an O or what that is, to be honest with you, math wasn't my strongest suit, stands for the effective stellar velocity dispersion. But the black hole in LRG 3-757 doesn't play by these rules. This black hole's mass is about 1.5 standard deviations above what the MBHOE relation would predict based on the velocity dispersion of 366 kilometers per second. That's a significant outlier. It suggests something unusual happened in the galaxy's past, or it's still happening now. Because again, this image that we're looking at that galaxy, that's how the galaxy appeared 5 billion years ago. So it may, my guess, it probably looks relatively the same now as it did back then, but I mean, who knows? So several theories might explain this deviation. One possibility is that LRG 3-757 underwent a dramatic history of mergers. In other words, lots and lots of galaxies smashing into it. And that's what allowed the black hole to balloon up to as big as it became, because it was just gobbling up tons and tons of matter, stars, gas, dust, all kinds of things just funneling right into that black hole. And the more matter it eats, the larger it gets. And if that were how it was able to grow to that size, one could only imagine the absolute epic quasar that thing must have been emitting for a long period of time, or a blazar, or whatever it was that it was emitting. It was probably insanely bright and intense, which quasars and blazars, they also, they very strongly hinder stellar formation inside galaxies. Whenever a large quasar were to fire off, which this one undoubtedly did, for it to grow to the size it did, it was firing tons of energy out from its polar region, and that just it just blows tons of gas and dust out of the galaxy. And stars, in order for stars to be born, they need gas, they need dust, they need those materials in the galaxy in order for stellar formation to occur, with nebulas and all that fun stuff. So yeah, I can only imagine. But anyway, several theories. Let's see, dramatic history of mergers. So during such events, central black holes from each galaxy can eventually merge, while gravitational interactions fling nearby stars outward, a process known as scouring. This can inflate the black hole's mass without increasing the average stellar speed. Another explanation is that AGN feedback, when an actively feeding black hole pumps energy into its surroundings, it disrupts star formation and changes the internal structure of the galaxy. There's also a chance that this black hole is a fossil remnant of an ancient quasar, an early universe black hole that grew rapidly by consuming large amounts of matter. That would probably be my guess. In this scenario, LRG 3-757 could once have been far more active, with the black hole gaining mass much faster than its surrounding stars could evolve. Yeah, I'm almost certain that's probably what happened. I mean, look, that image was taken 5 billion years ago, which means, what was that, like 8.72 billion years after the Big Bang first happened. That's how old this galaxy was, roughly 8.72 billion years after the Big Bang. That's a pretty short amount of time for a black hole to get 36 billion solar masses. So my guess is that it probably gobbled its way up to that size. I mean, that's just my opinion, but I'm almost certain that's probably what actually ended up happening, which allowed it to grow to this absurd size. That places it significantly... Oh, wait, hold on here. Let's see here. This study adds to the growing list of ultramassive black holes that deviate from the expected galaxy black hole scaling laws. But what makes this finding special is its distance. We see the cosmic horseshoe as it was over 4 billion years ago. I believe it actually said 5 billion years up there. But anyway, this places it significantly earlier in the universe's timeline than most direct mass measurements of supermassive black holes. It is also one of the most massive black holes ever directly measured at any redshift. So they're going to be including new tools to study this further. With telescopes like Euclid already scanning the sky, researchers expect to find hundreds of thousands of new gravitational lenses in the next 5 years. That is awesome. Many of these may host similarly massive galaxies with hidden black holes that challenge our understanding of galactic evolution. Yeah, I mean, like I said, gravitational lensing, especially as strong as this one, I mean, I would assume the bigger the black hole, the stronger the gravitational lens, if there's a galaxy directly behind it. Just because there's a massive black hole there doesn't mean that a gravitational lens is just going to happen no matter what. There has to be a galaxy directly behind this one in order for a lens to occur. Because again, light is bending around the galaxy and then projecting this lens around the edge of that galaxy thanks to the gravity from that insanely large black hole. So let's see here. Many of these may host similarly massive galaxies with hidden black holes that challenge our understanding of galactic evolution. With upcoming tools like the Extremely Large Telescope, scientists will be able to measure stellar dynamics with far greater precision, even in galaxies that are billions of light years away. This new era of discovery promises to deepen our understanding of galaxy evolution and the interplay between baryonic and dark matter components, the authors concluded in their paper. The study is published. The online journal ARXIV. So anyway, yeah, what a great discovery. Again, they first discovered LRG 3-757 back in 2007. Let's see, there's a couple more images that I pulled up on Google. Basically, it's just the same image, essentially. But I did come across this on NASA that also describes this galaxy a little further. Let me see if I can blow this up a little bit. So the Einstein ring, LRG 3-757, this is on science.nasa.gov. This interesting galaxy imaged by NASA's Hubble Space Telescope is one of a group of galaxies called luminous red galaxies. It has an unusually large mass, some 10 times the mass of the Milky Way. However, it's actually the blue horseshoe shape that circumscribes the red galaxy that is the real prize in this image. This blue horseshoe is a distant galaxy magnified and distorted by the strong gravitational pull of the massive foreground luminous red galaxy, which is, this orange ball here. Called an Einstein ring, this lensed galaxy required the exact alignment of the foreground and background galaxies, making this object's name the cosmic horseshoe particularly apt. The cosmic horseshoe is one of the best examples of an Einstein ring. It also gives us a tantalizing view of the early universe. The blue galaxy's redshift is approximately 2.4. This means we see it as it was about 3 billion years after the Big Bang, which is this galaxy that's curved around it. So this galaxy curved around it is roughly 11 billion light years away from Earth. So just to give you an idea of how, to the naked eye or to the untrained eye, more specifically, it just looks like a blob. But, I'm sure for those who are more well-read in astronomy, you can see like how important that is, because this galaxy being over 10 billion years old, you can see the detail in it. Like I said, like it almost looks like this might be the center region of the galaxy here, maybe here, possibly there, and maybe over here, something like that. It looks like you can almost see, 2, 3, maybe even 4 different images of the same galaxy that's been lensed around this galaxy here. And what's so cool about it is that you can see the detail of this galaxy, despite the fact that it's over 10 billion light years away. Even James Webb, I don't believe, can image a galaxy nearly this detailed from that far away. So that's pretty amazing. And that's why it's important for us to take a look out there and see if we can find more lensed galaxies, to see if we can study them and get more details as to their formation. I'm sure they could probably run computer models from the details of this galaxy, and they could probably end up picturing it together like a puzzle to paint a pretty accurate picture as to what this galaxy really looks like if you were to remove this galaxy away and see what this lens galaxy actually looks like as an actual image. Hell, they probably could, run AI or something like that to make that happen at this point. Who the hell knows? So anyway, let's see here. Where was I? Let's see. There it is. The universe is now 13.7 billion years old. Astronomers first discovered the cosmic horseshoe in 2007 using data from the Sloan Digital Skies Survey. But this Hubble visible and infrared light image taken with the Wide Field Camera 3 offers a much more detailed view of this fascinating object. Now, I wonder if, not sure if James Webb actually was able to capture an image of that. I'm kind of doubting it. Let's see here. I'm just going to see if maybe, because it hasn't been in operation for very long, and I'm sure there's a very long list of things for James Webb to take a picture of. So this galaxy could be in the line of objects to be imaged by James Webb, but who knows? Maybe it is, maybe it isn't. James Webb has a very finite amount of time, and I'm sure there's probably 10,000 different things that are waiting for James Webb to get a picture of. But I'm going to guess and say probably not. But, you know, I've been wrong before. But no, I'm not seeing. I'm assuming that it probably would have popped right up, if anything, because this image was from the Hubble Space Telescope. So let me just do one last check. I'm gonna check Google and not Brave and see what that might bring up. But no, not looking like it. I'm assuming it would appear a lot more detailed than that if James Webb were to train its eye on that galaxy. Wait, I think that might actually be relating to the article I was just reading. I mean, yeah, that one does appear to be a little detailed, but the image is smaller, so that could also be why. I mean, I guess it wouldn't hurt to click on it. Yeah, see, that's basically the same article that I already read. I'm just trying to see if I can find a little bit more of a detailed image of that. A little better than what I ended up with. I mean, hell, I'm not even seeing the image at all on here. What the hell? So, but anyway, that's essentially the article that I got. That's all I got for this. I thought that was really fascinating that, you know, despite the fact that they took a picture of that back in '07, they have concluded that the ultramassive black hole at the center, 36 billion times the mass of the sun, and so far that's the largest one that they've been able to definitively detect and know exactly how large it is and where it is and how far is it and all that good stuff. So will that be the largest one they ever discover? I'm almost certainly, I really doubt that. I'm sure they're going to probably find something much larger than that, even though it's almost impossible to fathom how massive that really truly is. I mean, like Sagittarius A, that's the supermassive black hole at the center of the Milky Way. If you were to remove the sun and you put Sagittarius A in place of where our sun is, that black hole, the event horizon, which is the edge of the black hole, would swallow up, I believe, all the way out to Jupiter. That's how large Sagittarius A would be. And Sagittarius A, it's like what, like 10 million solar masses or something like that. Sag. I'm sure I'm spelling that wrong. Let's see. Hold on. Oh wait, hold on. Where did it say? 4 so basically 4.3 million with an M times the mass of the sun. So we're talking thousands of times larger than the supermassive black hole at the center of our galaxy. I mean, like many thousands of times larger than the one at the center of our galaxy. And like I said, Sagittarius A, which is a supermassive black hole at the center of the Milky Way, if you were to take out our sun and put it in the middle of our solar system, it would envelop Mercury, Venus, Earth, and Mars, and it may even extend out beyond Jupiter, but it would roughly be around Jupiter's orbit. That would roughly be about the size of the supermassive black hole at the center of our galaxy. And I can only imagine, like, it would gobble up way beyond Pluto, I would assume, if you took the one that we just covered. I already forgot what it was called. LRG 3-757. Yeah, that's not the easiest to remember. But yeah, anyway, I guess I'll just cut it there. I could just keep looking up stuff on and on, but I'll just leave it there. Just stick to the point of where I was getting at. But yeah, very cool. Largest black hole ever. So always interesting to read about. Till next time. See you later.